What's up, guys? This is Mr. Bond. Today we're going to run through the definition of the derivative, which is super exciting. This is really the beginning of actual calculus. So recall that the IRC is defined as the limit, as h goes to 0, of f of a plus h minus f of a all over h. And you guys have been practicing with this definition in class. It means that if you have a given function, there's a specific point on that function. Call that point a f of a. And we can calculate the slope of the tangent line that passes through that specific point. Now, you guys have seen these problems in class. They're a little bit tedious. So if we went through one of these, we'd find the slope of that tangent line. But what if I wanted to find the slope of the tangent line at that point, or that point, or that point, or that point, or even that point, or that point, right? We wouldn't want to have to keep using this IRC definition for all of these different x values, right? All of those different possible x's. So we're going to kind of switch things up a little bit here today. Recall that the a represents one specific x value. So when you're using that IRC formula, you are finding one slope on your curve. So we substitute in a number for a. But x, the variable x, it represents all of your x values. So we're going to do something crazy today. We're going to really mix this up a little bit. Instead of substituting in a number for a, we are just going to leave a as the variable x. And that's going to create the definition of the derivative, which you can see here below the IRC definition. The only difference between them is that the a's have become x's. So where we would normally have a number for a, we are going to leave the variable x for x. And why is this important? Because the IRC gives us one specific slope, whereas the derivative will give us all of the slopes, all over our curve, all at once. The derivative is fantastic. We're going to keep the notation pretty simple for right now. We can't jump into derivatives yet. I know it's very exciting, but we have to look at the notation before we do anything too fun. So our notation, basically, depending on what your function starts out as, determines the notation that you have to use for the derivative function. So you guys can see some pretty common types of function definitions on the left-hand side, and the corresponding derivative notations that you would use on the right-hand side. The only one that I want to point out is that you get to choose between y prime and dy dx if your function starts out as y equals. These notations will make a little bit more sense as we proceed. All right, so here we go. We're going to calculate our first derivative. This is very exciting. I want you guys to actually try this one. I'm going to put the limit definition on the board. There it is. It's just like the IRC process, except you're leaving the a value as an x. Go ahead and give it a try. Okay, so either you gave it a try or you are just still here. Hello. We're plugging in x plus h into the original function. That means that it's going to become x plus h squared minus f of x. Well, what is f of x? F of x is equal to x squared. So that's why I replaced the f of x with an x squared. Super easy, barely an inconvenience. The x plus h got plugged into the x squared function that we started with. That's how I got the term on the left. If you plug in an x plus h with parentheses, you get that x plus h squared. So far, so good. Now we got to simplify that thing. So we do need to FOIL out the x plus h. Note that I'm maintaining my limit notation and my equal signs because I don't want to lose a ton of points on a quiz. Simplify that by FOILing out. Looks pretty good. What do we notice? The x squareds cancel out. Very nice. That leaves us with all h terms on the top. That will always happen. So I can pull out an h, leaving me with a 2x plus h all over h. We're pros at this point. The h's cancel out. I can plug in 0 for h in my numerator, and I end up getting 2x. So what does that actually mean? The original function was x squared. The derivative function, which represents all of the slopes on the x squared graph, is 2x. So that's it. We just did it. Instead of finding one specific slope, we just found every single slope for every single tangent line on the graph of x squared. But why is it 2x? Like, how does that work? Let's look at some examples. Okay, so we just went through that crazy process. We found our derivative function to be 2x. Our original function was x squared. Now we want to use this information to actually find some slopes. 2x represents every single slope on the x squared graph. The question is, how do I use it? Well, let's say I want to find the IRC at 7. I just plug in 7 into the derivative function, and I get 14. That's it. 14 is the slope of the tangent line, or the IRC, at x equals 7 on the x squared graph. That's the slope of that line. Let's do it again. I want to find the slope of the tangent line at x equals -5. What do? Well, I just went through all that work on that last problem, right, with this x squared function, to get my derivative function, to get my 2x. So I'm going to use it. I'm going to say that the slope of the tangent line is just the IRC at x equals -5, which means 2 times -5. I'm just plugging in -5 into my derivative function. The slope is -10. So once you find your derivative function, you get the slope everywhere. You just need to plug in the x value into the derivative function. Let's get the slope of the function at x equals 1. Same thing as the IRC. I'm just going to plug in 1 into my derivative function. That's it. So I could find the slope at every single x value. I just have to plug them in to the derivative function. So yes, the previous problem was a lot of work, but it gives you many solutions. Okay, so let's try another one of these derivative problems. This is a little bit more of a challenging one because it's a rational function, but we've done these before technically, right? We've done these with local limits. There's the limit definition of the derivative. Go ahead and find the derivative, pause the video, come back when you're ready for a solution. Okay, so my solution is going to take a couple of pages here. It's a little bit of a Friday night problem, if you know what I'm saying. Let's go through this. F of x plus h means that I plugged in x plus h into my function. F of x is just the original function. So far, so good. We're going to proceed. I need to get a common denominator. So I multiplied each fraction by the other's denominator over itself. I end up with this common denominator that I'm highlighting in red. Note that I'm leaving that h on the bottom every step of the way. Don't forget about that. The numerator of that complex fraction is right here in purple. So let's keep going. We're going to have to simplify that top layer, and then we're going to have to evaluate this complex fraction. You can pause again if you want another chance to see if you can get to the solution. Okay, so I simplified the top a little bit. I can actually cancel some stuff out. Things will always cancel nicely on these problems, so that's something you want to look for so that you know that you're doing it correctly. I end up with this complex fraction. Remember that if you have a over b over c, you can rewrite that as a divided by b times c. So I'm just going to essentially move the h in the denominator and multiply it by that common denominator that we got earlier. And you guys should notice right away that the h's are going to cancel on the top and the bottom. Again, stuff like that will always happen. It always works out very nicely. And because the h's cancel, I'm no longer going to get 0 over 0 if I plug in 0 for h. So I can plug in the 0 for h at this point. Your numerator is going to be the negative 3, and you're going to end up with two different x plus 2's on the bottom, or x plus 2 squared. And that's it. That's our final answer. I'm just going to use the same notation that the problem asked for at the beginning. dy dx is equal to negative 3 over x plus 2 squared. What does that solution mean? It means that if I want the slope at any x value on my original function, I can plug in that x value into that derivative function. I hope this was helpful. Definition of derivative is tricky because there's a lot of algebra involved, but if you guys keep practicing, you guys can all excel. What a happy note to end on.